là con nhỏ này nó không học nổi, nó toàn buồn ngủ. Thầy nói với lại anh chị Tiền, thầy nói với chị Tiền với anh chị Tiền, cái chị Tiền nói
em một là nghe chính xác, còn nếu mà nó đã qua một cái
chị Tiền nói
trung
gì?
gian filter
Chị Tiền nói gì?
giỏi lắm là em tin 60% thôi.
Em nghĩ là do thầy Binder coi điểm á.
Có vẻ là như vậy. Tôi nói là con nhỏ này nó học ở buồn ngủ, nó học. Nhưng mà em có mở mắt không? Không có nhắm mắt không? Không có đâu nào nào.
Singer.
I need to make sure that the camera is on. So it is recording now, right?
Okay, I would suggest that we do start the afternoon, and then the other two I'm sure will be there momentarily and not miss too much. So what we'd like to do now in the afternoon is first talk about estimation methodology for autoregressive models, and then we'll of course also start to go into Stata to start implementation of the in-sample analysis, including estimation of autoregressive models. That will let me talk a bit about principles of forecasting, develop how we calculate and how Stata will calculate for us forecasts of variables on the basis of autoregressive models, and implement that in Stata as well. That may take up pretty much the afternoon, but if we have more time, we'll extend into adding moving average components to AR models as well, so to look at autoregressive moving average ARMA models. But we'll see how much time will allow us to get into that still this afternoon. So starting point here for the estimation is again the write-up of the Pth order AR model that we had looked at last in the morning, yt as a function of p lags of itself, an intercept term, and the IID shock term. Question that we now want to answer is how to estimate the model parameters. Right? That's of course, even if we haven't discussed yet specifics of forecasting, clear that if we want to do any forecasting, we'll have to have parameter estimates in practice in order to understand how, on the basis of the in-sample evidence, yt depends on the lagged values in particular. That will require estimates of the slope coefficients, the phi j's in that formula for the AR model. Excuse me. The easiest way to go about estimation is to generally think about, is the model that we are currently analyzing fitting within to the framework of a linear regression. That's always the starting point of any econometric estimation, if possible, right? Then we just apply estimation techniques that we know from the context of default linear regression analysis. That is, in other words, if it is possible to estimate a model by OLS, then that sure seems the most straightforward and immediate way to go about it. So in that sense, can we think of our ARP model as being a special case of a multiple linear regression model that I wrote down in 26, write yt as a function of an intercept term, k regressors, capital K regressors, x1, x2 up to x capital K, plus the disturbance term, as we call it in that context, epsilon t, but of course that's just the same thing as the shock term in an AR model. Right, and so at first it seems, yes, this is pretty much the same thing, because what is the first regressor? Yt minus 1. What is the second regressor? Yt minus 2. What is the capital Kth regressor? Yt minus p. So we have the case where we have that the number of regressors, capital K, is just p, the lag order of this ARP model. And that basically all the regressors are lags of the dependent variable itself, right? Again, yt minus 1, yt minus 2, yt minus p. And that we have as the disturbance term, again, this ID term. So the default orthogonality condition that we had in linear regression analysis, namely that the disturbance term should be orthogonal, or at least uncorrelated with the regressors, that seems satisfied for this model, right, by design, because the disturbance term, or shock at time t, is independent over time, independent from any of those lagged values of y, right? And so that seems like we have a linear model, and the core orthogonality condition, zero conditional mean assumption, as we, I think, also called it in September, October, that is satisfied. And if you recall what we said in September, October, what property we can establish in that case, the general linear functional form holds plus that orthogonality, we then know that the OLS estimator is gonna be consistent, right? Consistent means that in large sample, the probability that the parameter estimate is equal to the true parameter value for each and every one of those parameters is 1. In other words, the parameter estimates converge towards the true values in large sample, right? Consistency was a large sample property that as the sample size becomes large, in our context, of course, sample size now being the time dimension, right? That we have many observations across time. If that number of observations across time hypothetically, theoretically tended to infinity, we do know that our parameter estimates converge to the true values. And that's very nice. But as we'll see when we move to Stata, when you look at AR, but also later on these ARMA models and so forth, it doesn't do OLS. It rather calculates a maximum likelihood estimator. And you can suspect there's a good reason for it. And what is the reason for it? We'll discuss now that while the OLS estimators of the slope coefficients in the ARP model are consistent, they are unfortunately not unbiased. Right, when we talked about linear regression, September, October, hopefully you still remember BLUE, B-L-U-E, Best Linear Unbiased Estimator. And that required more than the condition in 27. If you translated what we had back then into the time series setting, for the OLS estimate of the slope coefficients in the linear regression model to be best linear unbiased, you needed a stronger orthogonality condition, namely the orthogonality condition that the error term would be uncorrelated with the regressors across all time periods. It didn't come up in September, October this way, right? Because in September, October, we were talking about cross-section regressions. And so we said that the disturbance term needs to be uncorrelated with the regressors across all individuals. And that seemed a relatively innocuous assumption to make. Here, this is now a bit of a different thing, right? Because if we think about the regressors across all time periods, from the first time period to the very last in period capital T, this also means that the disturbance term would have to be uncorrelated with the current period y, with the next period y, y in period t plus 2, and so forth, right? Because if you think about writing down the model, right, we have, in the case of, let's take it to a simple AR1 without intercept, our original model would be yt equal to phi yt minus 1 plus epsilon t. Let's define the sample periods. Suppose we started that model in period 1, right? I'm not now writing down 1970 month 3 or something like that, just generic notation. It would start in period 1, so that the first model is y1 equal to phi times y0 plus epsilon 1, first time period. And then let's suppose the sample runs to period capital T. Right, then for the second time period, we'd have y2 equal to phi times y1 plus epsilon 2, all the way to the last time period, y capital T equal to y capital T minus 1, pre-multiplied by phi plus epsilon capital T. When, of course, anywhere in between, we'd have yt equal to phi yt minus 1 plus epsilon t. So if you think about all the regressors, right, what is the counterpart to all the regressors, x1 to x capital T in the specific AR model? All the regressors is just the set from y0 to y capital T minus 1. And that therefore for sure includes also yt plus 1 yt plus 2, and so forth. And of course, the shock in period t in gel does have an effect, right, on the current period y, but also on future y's. So this is not orthogonal, right? This will be correlated. The whole point in the time series model is that the shock in the current period may not just have an impact also on the current y, but also on future y's, right? So this is for sure going to be correlated. And even in the case where the shock in future periods was already having a zero impact, in the current period by design it has an impact, right? Yt is a function of epsilon t with the unit coefficient. So for sure, this orthogonality condition does not hold. If you want to put that into plain wording, right? Why does it not hold? Because our regressors, yt minus 1 is the one regressor. Relative to yt, it's predetermined. Yt minus 1 predetermined means it's determined prior to us determining yt, right? Yt minus 1 was determined in period t minus 1, and then yt is determined in period t. So in that sense, we say the regressor is predetermined, but it's not strictly exogenous. And when we're working in cross sections, right, this again, the strict heterogeneity assumptions seem perfectly fine. That we have a disturbance term that's just reflecting all the random stuff, purely random stuff, that's not systematic, that's not part of the regressors, but now we're in a different framework. We're in a time series setting, right? So this is a very different thing, and certainly this assumption cannot be presumed to hold. Whereas in cross sections, again, the counterpart seemed pretty fine, because there we didn't talk about regressors across different time periods, but we talked about regressors across different households or different firms or whatever the involved units were in a cross section. So that's, and I presume that Professor Hassler already stressed that a lot upon you in his course. That's where time series econometrics is different, and without any prejudice to microeconometrics is more difficult, because you have this intertemporal dependence. That means that this default orthogonality condition that at least in our cross-section regressions we keep using until we start talking about endogeneity because of simultaneous termination, instrumental variables estimation, and so on. That's the default assumption in cross-sectional econometrics. We cannot use that anymore now in the time series setting. So how does the maximum likelihood estimator help that the data will calculate? Let's set it out. And when we set it out, we'll understand what is the core difference as to what maximum likelihood does do, what OLS doesn't do, and why maximum likelihood will turn out to be unbiased even in finite sample. Of course, also be consistent as OLS in any case in large sample, but be clearly preferable in finite sample, because it's going to be unbiased in contrast to the OLS estimator. So let's do that step by step. The next few slides, if you have sharp memory, you have seen before in my course in September, October, so I'll go through those briefly just to jog your mind again on maximum likelihood estimation, right, so that you're back into it. But I didn't forget that I talked about this in September, October. That's what I'm trying to emphasize, right? So let's go back first again in terms of thinking about maximum likelihood to a elementary statistics example, before we get, of course, to the time series setting to understand what we need to do to construct a proper likelihood estimate and get, again, some intuition as to why this is a very promising estimation technique, right? And so a very simple example that we have a bowl that contains balls of two colors, a total of capital N balls that are either red or white. And that we are drawing the balls from this bowl with replacement, so that each draw is independent from the previous draw, because the number of red and white balls in each draw is exactly the same. We have the following notation. Yt is equal to 1 if we happen to draw a red ball, and yt is equal to 0 if we happen to draw a ball that is white. The probability that a ball that is drawn is red, we denote as pi. Just notation. Now, suppose that we happen to draw n1 red balls, and therefore if we have n draws, we must of course draw n minus n1 white balls. What is our inference about pi? Of course, we all recall, right, that if we are now asked the question, what is the probability that a ball in this bowl is red? Of course, we'll estimate it as n1, the number of red balls drawn, divided by n, the total number of draws, right? And that will be our maximum likelihood estimator. But let's see how maximum likelihood gets there. That's the key point of this simple illustrative example. And so we call that what maximum likelihood does do is it formulates the true probability distribution that's generating the data. And the nice thing about this example is we really know the true distribution, right? Not like in economics that we write down a model, but we probably think that's at best an approximation to the true model, but here we really know literally the true model, because if we draw with a replacement, we know that each individual draw is Bernoulli distributed, either red or white, two possible outcomes. That's a Bernoulli distribution. And repeated Bernoulli distributions are a so-called binomial probability distribution function. That's for sure the correct distribution in this context. And therefore, the probability of drawing capital N1 red balls and N minus N1 white balls, of course, is the probability of drawing a red ball, a ball being red, pi to the power of N1, pi times pi times pi times pi, N1 times, because we draw N1 red balls, times 1 minus pi, the probability that a ball is white, repeated n minus n1 times, right? That's the true probability distribution function. 32 is our likelihood, therefore, where the unknown is pi, right? In a likelihood function, it's not like in elementary statistics that you write down the probability distribution and then you just plug in some values of pi to calculate probabilities. That also seemed difficult at the time, but now we laugh about it. That seems too naive a task to do, right? To be given values of pi and then calculate some probabilities. Likelihood estimation is a little bit more sophisticated. You treat pi as an unknown, right? And we want to choose pi in estimation in that form that it maximizes the probability that the actual outcome was generated from the model. That is, we want to maximize this objective function in 32. To do that, we first take the log, right, to make it a little bit closer to linear, this model, have an easier task of writing down the first order conditions and solving them. So we first take the log of 32, that is in 33, and then differentiate with respect to pi, our unknown parameter, to maximize the probability that the data were generated from the model. We take that first order condition, solve it for pi, that's our likelihood estimator, right? N1 divided by n. Again, this is not the surprising thing here, that we estimate the probability that a ball is red as the number of times we did draw a red ball among all of our draws. But it's good that we get exactly what we should get, right? We don't need likelihood here, but likelihood still gives us the right answer. And now we can transfer this principle, of course, now back to our order regressive models. But just to be sure, everybody happy again about what likelihood does do, what the principle is, and now it's about applying that principle to order regressive models. Okay, so, and by the way, also one more slide from September, October. Formally without proof, we can show that this likelihood estimator is consistent, asymptotically normal in general cases, well beyond the AR models too, under some technical regularity conditions. And if we don't know the true distribution, but use, for example, the normal distribution in the context of linear regression models or AR models, then we call our estimator the so-called quasi-maximum likelihood estimator, right? Even if you don't know the true distribution, pretend that you knew it, go down to normal, but it's not normal under certain technical regularity conditions. This likelihood estimator is still consistent and asymptotically normal. Okay, so now let's apply it to our autoregressive model in 37. Here in 37, I've basically said, very much like I had here on the whiteboard, that the timing is such that the first y that we observe is y0. So we can first time write down the model for period 1. y1 is equal to phi times y0 plus epsilon 1. Right? I can't write it down for an earlier period. I couldn't write down y0 is equal to phi y minus 1 plus epsilon 0 because I don't observe y minus 1. Of course, you could also say observe y minus 1, but you have to make some assumption, right? What's the first y that's observed, and maybe 0 is a natural way to initialize things in an abstract form, and that's why we use that kind of timing, and again, let the sample run to capital T. You'll see where this timing now matters. Again, it's not important whether you start in period 0 on period minus 20 or on period 50. I just use 0 because it seems easy in terms of notation and a pretty natural initialization, but of course you could start in any other time period, then you'll have to, however, modify all of the subsequent derivations, and you'll see that as we work through it, that we really have to be a bit careful about being very clear about what's the initial value, in which time period do we have the model for the first time. That's important that we are very explicit about it, not the specific period, but that we are explicit about exactly where do we start. Okay, now, if you think about the joint probability distribution function of all of these observed values of y, right? Y is our endogenous variable, the dependent variable, so we care about the joint probability distribution of all of the observed y's, that by definition now are y0, y1, all the way to y capital T. Right, so we need to write down the joint probability distribution function of y0, y1, all the way to y capital T. And then the likelihood function is going to pick the values of phi0, phi1, and sigma squared so as to maximize the probability that the actual data were generated from that model. But our job now is to write down the joint probability distribution function of y0, y1 to y capital T. And this is not that easy, if it ever was easy in the cross-sectional context, but in the cross-sectional context it was easier. Maybe not in probability settings, then we had some nonlinear transformation and so, but if you think about linear regressions, right? Why was it easier? Because independence in the cross-sectional dimension meant the joint probability distribution is just a product of the marginal probability distributions. That's not going to work here now, right? Because the y's are dependent over time. y1 is not independent from y0. y2 is not independent from y1. So the joint probability distribution for sure is not just the product of the marginals. That's the additional complexity. So how to get this joint density? In 38, I first write down, right, again, that the likelihood function is just going to be that joint density. We'll probably have it in logarithmic form again to get closer to a linear setting. But if we said, well, y0, y1, y2, all the way to y capital T, they're not independent. Let's just put that joint density into Stata or any software and just tell Stata, go ahead, maximize it. I don't think you'll get an answer in finite time and maybe not even in infinite time, because even if the sample is not that big, right, later to make things concrete, we'll have quarterly data, or not initially monthly data on the federal funds rate. That's typically the most high frequency dimension that you can think of in a macro setting, that if you want to link the federal funds rate to other monthly observations, that's the highest frequency you can go about. And so we'll have, the thing ahead, I'll have data in the end from about 1970 to April 2005, right? That's the latest data that we can have. 2025, April 2025. So that's about 55 years of data. Even if you use the whole sample, 55 years of data times 12 observations, a bit more than 600 observations. That's capital T. So if you wrote down this joint density, what would be the size of this variance covariance matrix? 600 something by 600 something. And there's no software that can invert accurately matrices of that dimension. Unless they were diagonal, but they're not diagonal, right? Because these are dependent observations over time. Dependent, not independent. There's no way that you could do it. However good your software is, we can invert matrices of dimension 5 by 5, maybe still 10 by 10, and then I think it gets a little bit less clear, maybe 15 by 15 or 20 by 20, but for sure not 600 or more by 600 or more. That's just not feasible. As good as numerical software is, that's just not feasible to do that kind of inversion with any reliable degree of accuracy. So we can't just say, let's leave it at that and